We're going to talk about applications involving charged particles moving in a magnetic field. A charge moving with a velocity v in the presence of both an electric field E and a magnetic field B is described by two particles in a field model. It experiences both an electric force, which is QE, and a magnetic force, which is QV multiplied B. The total force, called the Lorentz force acting on the charge, is F equals QE plus QV multiplied B. Velocity selector. It's used as velocity filter for charged particles to select them based on their velocity. This device uses crossed fields to select only those velocities for which Fb equals Fe. When Fb equals Fe, as mentioned before, QVB equals QE. From this we can conclude that V equals E divided by P. When Lorentz force is higher than electric force, the velocity is too high. When electric force is higher than Lorentz force, the velocity is too low. The mass spectrometer. A mass spectrometer separates ions according to their mass-to-charge ratio. In one version of this device, known as Bainbridge mass spectrometer, a beam of ions first passes through a velocity selector and then enters a second uniform magnetic field B that has the same direction as the magnetic field in the selector. Upon entering the second magnetic field, the ions are described by the particle in the uniform circular motion model. They move in a semicircle of radius r before striking a detector array at P. If the ions are positively charged, the beam deflects to left. If the beams are negatively charged, the beam deflects to right. We can express the mass-to-charge ratio as m divided by q equals r multiplied p naught divided by v. Using this equation, m divided q equals r p naught multiplied p divided by e. Therefore, we can determine mass-to-charge ratio by measuring the radius of curvature and knowing the field magnitude b, p naught, and e. The magnitudes of the two fields are first adjusted to produce an undeflected beam. When the magnetic field is turned off, the electric field produces a measurable beam deflection that is recorded on the fluorescent screen. From the size of the deflection and the measured values of E and B, the charge-to-mass ratio can be determined. The results of this crucial experiment represent the discovery of the electron as a fundamental particle of nature. The cyclotron. A cyclotron is a device that can accelerate charged particles to very high speeds. The energetic particles produced are used to bombard atomic nuclei and thereby produce nuclear reactions of interest to researchers. A number of hospitals use cyclotron facilities to produce radioactive substances for diagnosis and treatment. Both electric and magnetic forces play key roles in the operation of cyclotron. The charges move inside two semicircular containers D1 and D2, referred to as Ds, because of their shape like the letter D. A high-frequency altering potential difference is applied to the Ds, and a uniform magnetic field is directed perpendicular to them. A positive ion released at P near the center of the magnet in 1D moves in a semicircular path and arrives back at the gap in a time interval t divided 2. The frequency of the applied potential difference is adjusted so that the polarity of the Ds is reversed in the same time interval during which the ion travels around 1D. If the applied potential difference is adjusted such that D1 is at lower electric potential than D2 by an amount V, the ion accelerates across the gap to D1 and its kinetic energy increases by amount QV. It then moves around D1 in a semicircular path of greater radius, because its speed has increased. After a time interval t divided 2, it again arrives at the gap between the Ds. By this time, the polarity across these has again been reversed and the ion is given another kick across the gap. The motion continues so that for each half circle trip around 1D, the ion gains additional kinetic energy equals to QV. When the radius of its path is nearly that of the Ds, the energetic ion leaves the system through the exit slit. The electron's operation depends on T being independent of the speed of the ion and of the radius of the circular path. We can obtain an expression for the kinetic energy of the ion when it exists the cytoskeleton in terms of radius r of the Ds. We know that V equals QPR divided by M. Hence the kinetic energy is K equals half mv squared, which equals Q squared multiplied P squared multiplied R squared divided by 2M. Now you can check your comprehension. Another example to check your comprehension. This was for today's concept and thanks for your listening.